Concavity and the second derivative test. In the last lesson, you may recall that when we talked about intervals on where a function is increasing or decreasing, that I pointed out that there were a couple different ways that a function could increase. All of these slopes of the tangent line here have positive slopes, but these also have positive slopes. So there are two different ways for a function to increase. Additionally, there are two different ways for a function to decrease. All of the slopes of the tangent lines here are negative, and similarly here. And concavity will discuss what the difference between this type of increasing is and this type of increasing is. In the second derivative test, we will use simply to determine where there are relative and absolute extrema again, just like the first derivative test, but it uses the second derivative. On with the lesson. Concavity. The graph of a differentiable function y equals f of x is concave up on an open interval I if the derivative is increasing on that open interval I. And, or, the graph can be concave down on an open interval I if the derivative is decreasing on the open interval I. What this means, these words here, concave up and concave down, these both describe f of x. And we are using information about the derivative to tell where the original function is concave up and concave down. So essentially what we're doing is we're looking at the first derivative, the intervals of the first derivative where it is increasing or decreasing. So this is going to feel very similar to what we were doing with the increasing and decreasing for the original function using the first derivative, but now we will be using the second derivative to tell where the original function is concave up and concave down. So back to the last slide, when you see a graph or a portion of a graph that looks like this or looks like this, this is where we tell the difference between those two different options for increasing and those two different options for decreasing. So both of these are concave up. And that's because just for this little portion of the graph here, another way to think about it is that the graph is opening up, and here the graph is also opening up. We'll do another bit of a graphical example on the next slide. But then for these examples over here in blue, these graphs are concave down. And you can see that it looks like just for these little portions right here, the graph is quote unquote opening down. So let's take a look at a different graphical example on the next slide. So to get a more intuitive idea as to what concavity is and what concave up and concave down means, what I want you to do right now is starting right here where this laser pointer is and to the right. I just want you to cover that part of the graph up with your hand really quickly. And then we're just going to be concentrating on this part to the left here. Now if you look, it looks like this part of the graph is trying to open up. And what that means is that from right about where I was telling you to cover and to the left, this will all be concave up. And to the left, from here, of that point, it looks like this part of the graph is trying to open down, which means over here to the right of this point, this would be concave down. And where the concavity changes, this point right here, is a very special point, special enough to get its own name. Points of inflection. A point, c comma f of c, where the graph of a function f has a tangent line and where the concavity changes. So just like in that last example, there would be a tangent line, which means more or less that the graph is differentiable. Where the graph has a tangent line means where the graph is differentiable, and where the concavity changes. So in that last example, the concavity changed from being concave up to concave down at that red point. So what you will do to find points of inflection are to first find the secondary critical values. And I give it this name, secondary critical values. That's because you are finding the critical values of the second derivative. You can see what that is over here. Then you will make a sign chart, and maybe I should make a note here that you will be using f double prime of x and the values from step 1. And then you will list the ordered pairs where the concavity actually changes. So the next couple examples that you will see, we will be looking at where a function is concave up and where it is concave down, and we will also be identifying points of inflection. Find the intervals on which the function is concave up or concave down, and list any points of inflection. So the first thing we need to do here is we need to find the first derivative. I'm going to find the first derivative over here like this. And it looks like we just get to use the power rule here. So this will be 3x squared minus 3. The next thing we need to do is go ahead and find the second derivative. So here I'll have f double prime of x. And again, the power rule can be used here. And when you find the derivative of the derivative, you end up with 6x. So what happens at this point is that we need to find those secondary critical values. And you can find those secondary critical values by first finding where the second derivative is undefined, and this second derivative is defined everywhere. And the second way to find the critical value is to set the second derivative equal to 0 and solve for x. So this tells us our secondary critical value, which I'm going to abbreviate secondary critical value, is x equals 0. That's the only critical value we have here. So what we can do now is make a sign chart. Put that critical value here. In this case, it's 0. And I'm going to pick a test value to the left of that. I'm going to call it -1. And I'm going to pick a test value to the right of that. I'm going to call it +1. You can pick any number you want, as long as it's to the left of 0 and to the right of 0. From here, what you will want to do is evaluate the second derivative at these values. F double prime of -1, f double prime of +1. And it's easy enough when you substitute -1 in for this x over here, you end up with a -6. That is less than 0. And if you substitute +1 in for the 6 over here, you get a +6. 6 times +1 is +6, which is greater than 0. So what that means is that you are concave down to the left of 0, and not you, the graph is concave up to the right of 0. So we can make our little notations find the concavity. So concave down from -infinity to 0, and concave up from 0 to infinity. Now that's part of it. The other part is this critical value here, this secondary critical value. Did the concavity change? Well, let's see, it went from being negative concavity or concave down to a positive concavity or concave up. So yes, at this value 0, the concavity did in fact change, which means there will be a point of inflection here, which I'm going to abbreviate POI, point of inflection. So to find out where the POI is, if you substitute 0 back into the original equation, original function, then you can find the y-coordinate for the point of inflection. So if you substitute 0 in here for x and here for x, you'll end up with a y-coordinate of 3. So the point of inflection here is 0, 3. So here are the answers for this particular example up here. For the second example, there is going to be a lot of work done, quote unquote, off screen, so that I can fit this problem on this slide. Again, the first thing we need to do down here for this example is to find the derivative. And the derivative, after it gets simplified nicely, is 32 minus 8x squared all over x squared plus 4, the quantity squared. And yes, you will have to use the quotient rule here to find this derivative. But then, that's not the end of it. We've got to find g double prime of x. And this ends up being a doozy of a derivative, so I would urge you to try it yourself. So you have x squared plus 4 to the 4th power in the denominator with 16 x cubed minus 192x in the numerator. All right, so with this second derivative then, we need to go through and find the secondary critical values, and you want to pay close attention to this x squared plus 4. There was no denominator for this second derivative up here, but there is here. And it turns out if you set the denominator equal to 0, just the denominator equal to 0, and try to solve for x, you'll end up with imaginary values. So there are no secondary critical values that will be obtained by setting the denominator equal to 0, or where the second derivative is not defined or not continuous. So this gives imaginary numbers, so that means we need to concentrate on the top. So in the numerator, we can set 16x cubed minus 192x equal to 0. It turns out you can factor a 16x out of each term. And so that gives you x squared minus 12 equal 0. And if you set each factor equal to 0, you'll end up with x equals 0 and x equals plus or minus 2 square root of 3. So here are your secondary critical values, which means that on a number line, I have to set up these secondary critical values. So there's one here at 0, there's one here at positive 2 square root of 3, and there's one here at negative 2 square root of 3. So then you can pick some test values as long as they are in each interval. So I'm just going to draw some pinky purpley lines right there. I'm going to make sure I do this part. There we go. And so I'm going to pick a number to the left of the negative 2 square root of 3, maybe call it negative 4. In this interval, maybe I'll pick negative 1, positive 1, and positive 4. And again, you evaluate the second derivative at these test values. So when you substitute negative 4 and negative 1 and positive 1 and positive 4 into this whole derivative, second derivative over here, you will see that you'll get values that are negative, positive, negative, and positive left to right. So that means this was concave down, then concave up, then concave down, then concave up. Well, that's really interesting. That is an interesting little pattern there. Anyway, from there, you can write the intervals of concavity. So this graph is concave up from negative 2 square root of 3 all the way over to 0, and again over here from positive 2 square root of 3 to infinity. And it is concave down from negative infinity to negative 2 square root of 3, and from 0 to positive 2 square root of 3. That being said, we also have some points of inflection here. In fact, 3 points of inflection here. Because at negative 2 square root of 3, the concavity changes from down to up. At 0, it changes from up to down. And at 2 square root of 3, it changes from down to up, again going left to right. So that means if you want to figure out where the point of inflection is, you take the value and you substitute it back into the original function. And the easy one to substitute in for x here is the 0. You will have a point of inflection at 0, 0. And when you substitute negative 2 square root of 3 in for x here and here, you'll end up with a value of, so negative 2 square root of 3, a value of negative square root of 3. And at the last point of inflection, you will substitute positive 2 square root of 3 into these x's and get the third point of inflection as being positive 2 square root of 3 comma square root of 3. So we have all of our answers for this stuff down here. And I just realized a little mistake. It doesn't change any of the outcomes of our answers. And that mistake is right here. This exponent 4, this is x squared plus 4, the quantity to the 4th power. That exponent needs to be 3. There is some cancellation that happens when you simplify the second derivative that should be the 3rd power in the denominator. That being said, on to the next part of the lesson. Second derivative test. Suppose f double prime, or the second derivative, is continuous on an open interval that contains x equals c, and that f prime of c equals 0, And another way of saying that is that the value c is a critical value. Then we have three different cases. In the first case, if f double prime of c is bigger than 0, then there's a relative minimum at x equals c. In the second case, if f double prime of c is less than 0, then there is a relative maximum at x equals c. And in the last case, if the second derivative at c equals 0, then the second derivative test fails, and you should use the first derivative test to see if there is a relative max or a relative min at x equals c. So there are three different scenarios here. The easiest one to remember is if you have a critical value and at that critical value the second derivative is also 0, then the second derivative test fails, and then you have to go backtrack and do the first derivative test. But the other two might seem a little counterintuitive at the moment, right? You think if in scenario 1 or in case 1, if f double prime of c is bigger than 0, then you might think bigger. Oh, bigger, that means maximum. It's bigger, maximum. Well, that's not true. There would be a relative minimum at x equals c. And that's because if you remember that the second derivative being bigger than 0 means a graph is concave up at that point. So if you're concave up, like this graph over here to the right, that means you will be a minimum value. So for scenario 2, if the second derivative is negative, that means the graph is concave down, which means it opens down in a sense. And that means you would have a maximum. So you have to remember that we're talking about the second derivative. And describing the original function in terms of the second derivative talks about concavity, or which way the graph is opening. So if you can remember these pictures, positive second derivative, concave up, means a minimum. Negative second derivative, concave down, means there's a maximum. Let's take a look at how this works in practice. In this example, we will use the second derivative test to find and classify all extrema for this function. F of x equals negative x to the fourth plus 6x squared minus 4. So what's really nice about the second derivative test is that we do not need the intervals of concavity for this. We just need to use the first derivative and find the critical values, and then evaluate the second derivative at the critical values. So let's go ahead and do that. Finding the first derivative, it looks like we're just going to use power rule here. So f prime of x equals negative 4x cubed plus 12x. All right, that's not so bad. So we have the first derivative, that's the first step, and then we need to find the critical values. So we're using the first derivative, we're going to set it equal to 0 and solve for the x. So negative 4x cubed minus plus 12x equals 0. Factor out a 4x. In fact, let's factor out a negative 4x. That'll give you x squared minus 3 equals 0. And if you set this factor and this factor equal to 0, that tells you that you'll get some critical values of 0 and plus or minus the square root of 3. So these critical values are where potential extrema lie. So we could have a maximum or a minimum at 0. We could have a maximum or a minimum at positive or negative square root of 3, depending upon what the second derivative tells us. So let's go over here. Next step, we want to find the second derivative. And again, it looks like we're just going to be using the power rule here, so let's do that, and that will give negative 12x squared plus 12. And that's it. We don't need to set it equal to 0. We don't need to solve for x. That's it. We just need the second derivative. What do we do with this second derivative? We evaluate the second derivative, so f double prime of x, at the critical values. So what that means is that we come down here and we find f double prime of 0. Well, that's negative 12 times 0 squared plus 12, and that just gives us 12. Well, the fact that this number is positive tells us that at the x value 0, it is concave up, because that's what happens when you get a positive value for the second derivative. It's concave up. That means there is a relative minimum at x equals 0. And we can repeat this process. So f double prime of the square root of 3. That ends up being negative 12 times the square root of 3 squared plus 12, which is negative 24. And since this is negative, we will have a relative max at x equals positive square root of 3. And if you go through and do all of the work for the negative square root of 3, you'll also get negative 24, which is negative, which means there's also a relative max at x equals negative square root of 3. And without looking at a graph for this, we can only say that these are relative maxes and mins. Maybe we should draw out a sketch of what this graph looks like. So from a previous math course, I know that there will be a relative minimum at 0, so I'm going to put it down here. That's an x value. And I also know that I have a relative max over here at negative square root of 3 and at positive square root of 3. So I can tell right away that since this degree is even, that I know this graph will open down because of the negative in front. It'll open down to the left and down to the right. So let me put my maximums up here. So it's going to go down to the left, it's going to bottom out there, and it's going to go down to the right. So the only question we have is, are these maximums absolute? Or is one of them absolute and the other one relative? Well, we could think of this one of two ways. The first way is we can substitute positive square root of 3 into the original function and negative square root of 3 into the original function. And what will happen is you'll see that you get the same exact value for both. So you know then that these maxima are at the same height, which means both of them would have to be absolute maxes. The other way to see this is to notice that x to the 4th power, x squared, and technically over here on the end of the function there's an x to the 0. All of the x's have even exponents. This is an even function. So whatever happens to the left of the y-axis happens to the right of the y-axis. So since this is an even function, that means these maxima have to be at the same height. So not only do we have two maxima here, but they are both going to be absolute maxima for both. So this one is also absolute max. And that's because when you look at this graph, just a sketch up here, it's going to go down forever to the left and to the right. It's not going to just somewhere over here say, haha, I'm going to curl back up and not make sure you have an absolute max. No, we put these arrows here, it's going to go down both directions forever. So we have two absolute maxima here and a relative minimum. For this example, you'll see that we will be using the second derivative test to find and classify all extrema again. And this function should look familiar. So if you'll recall from a few slides ago that the first derivative is g prime of x equals 32 minus 8x squared all over x squared plus 4 to the second power. Just like a few slides ago when we were trying to find where this function is undefined, this is x squared plus 4. If you try to solve this denominator, or if you set it equal to 0 and try to solve for x, you will get imaginary values. So we can only concentrate on the numerator. So again, the first step is to find the derivative. The second step is to find the critical values. So we will set 32 minus 8x squared equal to 0. When you add 8x squared to both sides, we'll have 32 equals 8x squared. Divide by 8. That will give you 4 equals x squared. Square root both sides. That tells you x equals plus or minus 2. So these are the critical values, x equals plus or minus 2. And to use the second derivative test, we need a second derivative, first of all, but we also need to evaluate the second derivative at these critical values here. So if you will recall, the second derivative, g double prime of x, is 16x cubed minus 192x all over x squared plus 4, the quantity cubed. Now that we have that derivative, we can substitute these values, positive 2 and negative 2, into this function and get some values here. And we'll figure out if it's a relative max or a relative min. So we need to find g double prime of negative 2. So that is 16 times negative 2 cubed minus 192 times negative 2 all over negative 2 squared plus 4 cubed, which is negative 128 plus 384 all over negative 2 squared is 4, 4 plus 4 is 8, 8 to the third power is 512. Which is 256 over 512, which is 1/2. All right, that is positive. That means there is a relative minimum at x equals negative 2. For now, anyway, we're definitely guaranteed a relative minimum. It might be an absolute, but let's continue with this to see what happens. So that's step 4. There we go. So g double prime of 2 equals, let's see here, 16 times 2 cubed minus 192 times 2 all over 2 squared plus 4, the quantity cubed. So this time you're left with 128 minus 384 all over 512. And that equals negative 256 over 512, which is negative 1/2. So this is negative. That means there's a relative max at x equals positive 2, right? That's this value here. That's this value here. Cool. Are they absolute? Are they relative? Oh, well, it would help to see a graph of this thing. And as a matter of fact, it would help to see a graph of most functions when we're doing this. So I can draw a graph right up here on the upper right corner. And the graph of this will look something like this here. And I know this graph is going to look like this, especially to the left and to the right, because I know limit laws. I've learned calculus, and you've learned calculus along the way. So as x approaches negative infinity, because the exponent of x, the degree of the bottom is bigger than the degree of the top, this will tend back toward the y-axis as you go further and further left. And it's the same thing if you go further and further right. Since the degree in the denominator is bigger than the degree in the numerator, this will tend back toward the x-axis. Which means that if you come back down here, these aren't going to be relative max and relative min. These will be absolute max and an absolute minimum. One of the last couple topics here we will be discussing for this lesson is curve sketching. And this may feel familiar. One of the things that you've maybe seen in a previous math course is that you sketch the curve of some polynomials or a rational function, and we had to go through and do all of, check off a list of things that we needed to find, the first of which usually is finding the domain. And included in that is whether or not a function is even or odd, generally called the symmetry of a function. And then, like in a previous math course, you would find horizontal asymptotes and vertical asymptotes. So this is vertical asymptotes and horizontal asymptotes. Or maybe even a slant asymptote or oblique asymptote, depending upon who you learn this from. And then x and y intercepts. That was another big thing you learned about in previous math courses. So what's new to this? Well, in the previous many sections, we've been talking about ways to describe graphs using calculus. This is all new, and this is all involving calculus. So what's new? Well, now we're going to find the first derivative and the second derivative. And what we will use these for primarily is to find out where the function is increasing and decreasing. We use the first derivative for that. And we use the second derivative to find out where the function is concave up or concave down. In addition to that, we're also going to find any inflection points and make sure those get labeled. And we will come back to the first derivative and find the critical values and classify them as maxes and mins. So we can do all of this stuff, every last thing here in this list, just by looking at a function equation. And I think that's pretty amazing to do. We can just look at this, do a little calculating, and get a really accurate graph of what that function will look like. Let's take a look at an example. So in continuing with the theme of this section, this lesson, and the fact that I just kind of threw up a graph for this example last to justify there being an absolute max or min in the previous example, let's go through and find all of that information from the previous slide with this actual function. I mean, we found a lot of it already, the first derivative and the critical values and the second derivative and points of inflection. We just need the domain and range. Is it even or odd? These sorts of ideas to finish it out. So the first thing I want to talk about that we've been mentioning over and over and over again is that the domain here is all real numbers. And that's because the discontinuities just don't happen down here. X squared plus 4, if you set that equal to 0, and I've been saying this, so let me actually write it out here. If you take x squared plus 4 and you set it equal to 0, you'll get x squared equals -4, x equals the square root of -4, and because that negative is on the inside, this is imaginary. And if it's imaginary, then it doesn't hold a place in our world. We work in the real world, the real number world. So the domain here is -infinity over to infinity. And now for a lesson in even and odd functions that you may have heard before, maybe you've forgotten it, maybe you haven't even heard it before. That is, if you're dealing with a rational function, if you end up with something that is odd over even, or even over odd, then the entire fraction is odd. Consequently, if you end up with even over even, or odd over odd, then you're left with an entire fraction that is even. So if something on top and bottom is different, odd over even, even over odd, then it's odd. If you have even over even, or odd over odd, or the evenness and oddness match in the top and bottom, then the function is even. So what happens is that gives you a way to look at this fraction and determine whether it is even or odd. So in the numerator, if you replace 8x, if you replace the x with negative x, you end up with negative 8x. Remember, if f of negative x equals negative f of x, that's how you know something is odd. So the top here is odd, and in the denominator, if you replace x, so we have x squared plus 4, if you replace x with negative x, so negative x squared plus 4, and you get back what you started with, right? Negative x times negative x is positive x squared plus 4. So we just got back what we started with when we substituted in a negative x, like this. F of negative x equals f of x. The bottom is even. So that means the whole fraction g of x is odd. Alright, so we have a symmetry, we have a domain that takes care of the first point from the previous slide. We have pretty much done everything for points 2 through 5. We found the first derivative, we found the second derivative. The only thing we haven't done there was point 3, find out where the graph is decreasing and increasing. But we can come up with that pretty quickly. The only critical values for g of x were at x equals plus or minus 2. And you can set up a number line like this and put in your negative 2 and put in your positive 2. and then pick your test values. So I'm going to pick -3, 0, and +3, and do f prime of -3, f prime of 0, f prime of +3, and you can go back and check all of this. So I found all of this stuff to be decreasing, increasing, decreasing, which matches up with our maxes and mins, just like we found in the previous example. There's a minimum at -2, and there's a maximum at +2. Awesome. So we've got our intervals on which the function is increasing or decreasing. The only thing left we need to do now is find any asymptotes and find intercepts. So I mentioned in the last example that there was a horizontal asymptote at y equals 0 because the degree in the denominator is bigger than the degree in the numerator. So we already know that is there, y equals 0. And I explained it a little bit by limits. But there are no vertical asymptotes, and that is, we explained it already, but we explained it in terms of the domain. So there are no vertical asymptotes here because they would be imaginary. And there's nowhere to graph an imaginary vertical asymptote. So the very last thing we need to do here is find the x and y intercepts. The x-intercepts are when you set the numerator equal to 0. The y-intercept is when you set the entire thing equal to 0. And in this case, the x and y-intercept end up being the same thing. And that is 0, 0. And there are no other x-intercepts here because of that horizontal asymptote y equals 0. And there are no other y-intercepts because you can only have one y-intercept and still have a function be a function. So this is all the information we need. If you want to go back and look up where the function is concave up and concave down and all of this stuff, I urge you to rewind in the video to find all of that information because I will be using it on the next slide. So here is some information on the function that we are trying to graph, and I want to present the rest of the information, say when the graph is concave up and when the graph is concave down and increasing and decreasing and all of these different things in a table, but it's going to pop up on your screen all at once, and I will be sure to explain everything that's going on there. So here's the table. Oh wow, that is a lot of information. I'm going to put some lines in here to separate out the rows. There we go. So some explanation about what's happening on this table. I want to first draw to your attention what is going on with this left column with the x's. You can see that we start out with an interval where x is less than -2 square root of 3, and then x is equal to -2 square root of 3, and then we move to the right a little bit, say x is between -2 square root of 3 and -2, and then we continue to the right, and now x is equal to -2. Then we have an interval from -2 to 0, then 0, equal to 0. Then an interval from 0 to 2, then equal to 2, then an interval from 2 to 2 square root of 3. So all this is doing is showing you that x is moving from left to right, but at very specific values. You may recall that there were some points of inflection at -2 square root of 3, 0, and +2 square root of 3. So where you see the exact values, this is a POI. This number, or this row right here, is another point of inflection. This point here is another point of inflection. And that there are some other rows that have y-coordinates. So these rows with y-coordinates here, here, and here were all points of inflection based upon the x values. But these other rows with y values, here at -2 and here at +2, these are where there are extrema. And that makes sense. If you look at where the derivatives are, the extrema only happen where the first derivative is equal to 0, and all these other derivatives are less than, greater than, or less than 0. Okay, cool. What else do you know about these first derivatives? All of these derivatives up here are less than 0, less than 0, less than 0. That means the function is decreasing. That exactly is how it matches up if the function is to the left of -2 on the previous slide. Go back and look at it. To the left of -2, that function is decreasing, so the first derivative is negative. Awesome. Between -2 and +2, the function is increasing. Look at that. All of these first derivatives are positive. So between -2 and +2, where we have the extrema, the function is increasing. And then, after the maximum at 2, 2, if you go look to the right of +2 on the previous slide, all of the derivative values would be negative. So it is decreasing again. So decreasing, increasing, decreasing. As for the second derivative over here, this just organizes where the function is concave up and concave down. So remember, there was a point of inflection at this ordered pair right here. To the left of that, it was concave down. To the right of that, and to the left of 0, it was concave up, where the second derivative is positive, so on and so forth. So all of this stuff matches up with what we said. I just organized it in a table. Trust me, it'll help you a little bit later. So now we just have to come through and do this. So I'm going to plot the extrema over here at -2, -2, and +2, +2. So there are the extrema. I want to plot the points of inflection in this orangey color. So there's that at 0, 0. There's another point of inflection at -2 square root of 3, which is about 3 point something, and then negative square root of 3, so that's -1.7 about. So there's a point of inflection about right there. And there's another one about right here. Awesome. All right. So we're going to use the fact that this graph is odd in just a minute, just to make sure it matches up with what we're doing. The x-intercept is on y-intercept are already plotted here. I'm going to dash in a horizontal asymptote right here in pink. So there's a horizontal asymptote at y equals 0. I think that's everything. So what needs to happen from left to right is that I need to make sure that I'm decreasing but concave down. And I'm not going to cross this horizontal asymptote again. So if you're decreasing and concave down, that means from left to right you've got to be going down. Probably something like that. That looks good. So you can see that from left to right this graph is going down, but just this little portion of this graph looks like it's trying to open down as well. Or it's curling down, if you want to think of it like that. So then we need to look at the interval that's happening between -2 square root of 3 and -2. So that's right here. In this section, the graph is still decreasing, so we need, and that makes sense because we need to get down to this point, this minimum. We're not there yet. But now it's going to start looking like it's going to curl up. So I'm going to put a little bit of an upward curl. You may have to get close to the screen to see that, but there is a little bit of an upward curl starting at that point of inflection to the minimum. And then at that minimum, at that extrema, we will start increasing the graph. So the graph has to increase all the way over into x equals 2. That's how we're going to get to this maximum. but it looks like something's going to change here. So let's increase until we get to 0, 0. So we're still concave up and increasing. So that means opening up and increasing, or curling up and increasing. So something that looks like that. But then at 0, 0, the concavity changes. There's a point of inflection. So now I've got to draw this graph like it's going to open down. So let me see if I can do that. We're still increasing. You can see right down here that the graph will still be increasing between 0 and 2. And that's where we are. We're at 0. We need to get to 2. So it's still increasing, but now it's going to have this downward curl to it. And then at that point, when we get to x equals 2, that's the extrema, that's the maximum, all right? So then we need to curl, we need to start decreasing and still keep curling downward. Let's see, so it's going to look something like that until you get to this point here. And then after that point, 2 square root of 3 square root of 3, we will still be decreasing, but then looking like we want to curl upward. Let's see if we can do this here. So it's still decreasing, but it looks like we are starting to curl, and if this curl continued, we'd be curling back up, so concave up. All right, so there is the graph of the function 8x over x squared plus 4. Long, drawn out, hopefully very informative. I just have a couple more examples, much simpler examples, to get you through before you can go on and conquer the next lesson. So in this example, you're asked to sketch the graph that satisfies the following conditions, and this is exactly what I was trying to get at with the last one. It's just not in a table format. So the first thing you'll want to do is plot these points. So this is a different way to represent points. There's an x, and when you input an x, you get back a y. So the first thing you should do is plot the points. So 3, 1 is the first point. Negative 4, negative 3 is the next point. 0, 5 is a third point, and the last point is negative 2, 0. So we've got this information. I don't have any asymptotes, so I don't have to graph any asymptotes. That's awesome. Now we can just go on to where the graph is increasing or decreasing, concave up and concave down. Since here the derivative is negative, the first derivative is negative, I'm going to just come off to the side and label this as decreasing. And since this first derivative is positive, I'm going to come off to the side and label this as increasing. And the same thing with the second derivative. Since this second derivative is less than 0, it's negative. This is concave. I'm going to label it concave down, CD. And since this second derivative is positive, I'm going to call that concave up, or curling up. All right, so let's see, all we have to do is figure out what's going on here. So we're going to decrease from negative 10 all the way over to negative 4. I guess I should state that I want to graph this on the interval negative 10 to 6. That way you're not trying to figure out what happens at the end point. So it's a continuous graph. It is just on this little domain, negative 10 to 6. So you can come over here and start your graph at negative 10 anywhere, as long as you're decreasing between negative 10 and negative 4. So I know that this is going to have to go down to get to this point here. So I just have to decrease, 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 and right there I'm going to stop decreasing, right, at negative 4, and then I'm going to start increasing at negative 4, and I'm going to increase all the way over to 0. So the other thing we have to keep in mind is, will you be concave up or concave down as you are decreasing? Let's see, so negative 10 to negative 4, that is in this interval. That means we will be concave up. from here to here. So that means it's got to look like I'm curling up a little bit. So I'm going to draw the graph that looks something like this. So that looks like it's trying to open up. If you had continued that trend, it would look like it's opening up. All right. So then from -4, we have to go over to -2. We've got to get through that point. So between -4 and -2, it's clear that you will be increasing because -4 to -2 is in this interval. But also -4 to -2 is in this interval, which means you're concave up. So this will still keep curling up, which is nice. And then now we have to get from -2 to 0, an x value of 0. So between -2 and 0, it looks like we're still increasing here because -2 to 0 is on this interval. But -2 to 0 on this interval here means it'll be concave down. So it's got to look like we're trying to curl down a little bit. So at this point, it's going to look something like that. So then what? We have to get to this point over here at 1, 3. I realized now that I plotted that point incorrectly. Can I erase it? Nope. So forget that point right here. And the point is 3, 1. I think I said 3, 1 and then plotted it at 1, 3. Apologies. So let's see, to get from 0 to 3 on the on this interval from this point to this point, let's see, 0 to 3 is decreasing, so we know we're going to be going down. But look at this, 0 to 3 starts out concave down, so I'm going to go like this. I'm going to act like I'm going to curl down again. But then at 1, the graph becomes concave up. So I'm still decreasing and I'm concave up. So it looks like right there at that point, I'm stop curling down and start curling up. And then after 1, the rest of the graph is concave up. So starting here and to the right, the graph is concave up. And from 3, the graph is increasing. So as long as we're concave up and increasing all the way over to 6, you can't mess up this graph. So concave up and increasing, about right there. So this is what a graph looks like. We have to go through these 4 points right here, right here, right here, and right here. So it doesn't leave a whole lot up to the imagination, but I could have started, I'm going to pick a different color here, I could have started way up here and come down and gone through these points, just like the orange graph. So there, at that point, I've got to start being concave down, but still increasing, and concave down until 1. Maybe I would have stopped right there at that point, and then I would have been concave up for the rest of that, and maybe I would end a little bit lower. So you could draw multiple graphs for this particular set of characteristics or conditions. But we give you these ordered pairs here, 3, 1, -4, -3, 0, 5, and -2, 0, just to keep most of you on track.